Okay, in this class, I am going to talk about the next approximation method, that is the perturbation method. Perturbation method. Perturbation method. Okay, so we already learned one approximation method, that is the variation method, and this is the second approximation method that we are learning, that is the perturbation method. So, what is the meaning of perturbation? Perturbation. What's the meaning of this term, perturbation? Okay, this term means the deviation of a system from its normal state. Deviation from normal state. Deviation from normal state. Normal state. So, the deviation of a system from its normal state caused by some external influence. Okay, caused by some external influence. That is the meaning of perturbation. In quantum mechanics, the exactly solvable systems, exactly solvable systems are considered as unperturbed system, perturbed system. Okay, unperturbed systems. So the systems where Schrodinger wave equation cannot be solved, and such systems are considered as perturbed systems. Okay, so we have unperturbed systems and a perturbed system. So uh, perturbation means there is a deviation from the normal state, and the normal systems are the unperturbed system whose Schrodinger wave equation is exactly solvable, but sometimes due to some terms in the Hamiltonian, the Schrodinger wave equation cannot be solved exactly, and such a systems can be regarded as an unperturbed system. Okay, and we can take an example, and then you will understand what is meant by perturbation. Okay, for example, we are considering a oscillator sorry harmonic oscillator, and we have already learned the quantum mechanical treatment of the harmonic oscillator. And we construct the Schrodinger wave equation for the harmonic oscillator. We solved that Schrodinger wave equation in order to get the wave function and energy. Therefore, we can consider this as an unperturbed system. Harmonic oscillator is an unperturbed system. Okay, because the Schrodinger wave equation can be exactly solved. But now you consider an enharmonic oscillator. Okay, and enharmonic oscillator means there is a deviation from its harmonicity. Okay, and this enharmonic oscillator can be regarded as a perturbed system. So the harmonic oscillator, while harmonic oscillator is an unperturbed system, enharmonic oscillator is a perturbed system. Okay, it means that it is not possible to get the exact solution of the Schrodinger wave equation for the enharmonic oscillator. And we can take another example. For example, hydrogen atom. We have already solved the Schrodinger wave equation for the hydrogen atom. We got the exact solutions, means wave function and energy we got in the case of the hydrogen atom, right? But if it is brought in an electric or magnetic field, it becomes it becomes a perturbed system, because there is the interaction of the electron with the field. So if you are bringing the hydrogen atom containing the nucleus and the electron, this is a nucleus and this is the electron, and when it is not in the field or when it is isolated, there is only one type of interaction, that is the nucleus electron interaction, that will contribute one potential energy term to the Hamiltonian, and the Schrodinger wave equation is exactly solvable. But if you are bringing this to an electric field, okay, then this system is under the influence of the electric field, and there will be interaction of the electron and the nucleus with the electric field. That brings additional terms in the Hamiltonian. Okay, so the system becomes perturbed system. Perturbed system. But similar is the case when you are bringing this to the magnetic field. That is also going to disturb the system, and then the system becomes a perturbed system. Okay, so hydrogen atom, while hydrogen atom is an unperturbed system, the hydrogen atom in an electric field or magnetic field is a perturbed system due to the interaction of the electron or nucleus with the magnetic field or the electric field. Okay, that brings a perturbation in the system. Let us consider that psi n0 is the wave function of the unperturbed system, perturbed system. Okay, and en0 denotes the energy, means the ground state energy of the perturbed system, unperturbed system. Okay, and here n represents the state of the system. For example, if you are considering a harmonic oscillator, n is equal to 1 n when you are considering the ground state, but n will be 2 if you are considering the next excited state, right? So n represents the state of the system, psi n0 is a wave function, and energy en0 is the energy at that particular state. Okay, and this is for the unperturbed system. And in order to show that it is unperturbed system, we have used a superscript 0 here, right? This superscript 0 represents that this is an unperturbed system. So now we have the eigenvalue and eigenfunction corresponding to an unperturbed system, and this eigenvalue and eigenfunctions are of the Hamiltonian h cap 0. So this is Hamiltonian for the unperturbed system. Hamiltonian operator for the unperturbed system. So that we have an equation, a Schrodinger wave equation of the type h cap 0 psi n0 is equal to en0 psi n0. Okay, this is the Schrodinger wave equation for the unperturbed system. Here you can see that you can see the superscript 0 in all the terms, which represents that we are talking about the unperturbed system. Okay, and now we are considering a perturbed system, and in that case, when we are considering the perturbed system, we consider the wave function as mere psi n. Okay, so psi n is the wave function of the perturbed system. Okay, so you can see that there is no superscript 0. It means that it is of the perturbed system, and En is the energy of the perturbed system, and the Hamiltonian corresponding to that is h cap. So h cap is the Hamiltonian for the perturbed system. So for the perturbed system, we can construct an equation h cap psi n is equal to En psi n, right? H cap psi n is equal to En psi n. And now we have to closely look into the Hamiltonian of the perturbed system, h cap, the Hamiltonian of the perturbed system. And if you are looking into the Hamiltonian of the perturbed system, we can see that this Hamiltonian can be constructed from the Hamiltonian of the corresponding unperturbed system. Okay, I will explain once again. This Hamiltonian h cap can be constructed from the Hamiltonian of the unperturbed system. Means h cap can be expressed as h cap 0 plus lambda h cap dash. Okay, where h cap 0 is the Hamiltonian of the corresponding unperturbed system. For example, you want the Hamiltonian of a enharmonic oscillator. That Hamiltonian can be constructed from that of the harmonic oscillator, that is the unperturbed system. Okay, so you take the Hamiltonian of the harmonic oscillator and add some term with that, and then that will give the Hamiltonian of the perturbed system. Okay, so the perturbed Hamiltonian can be expressed as h cap is equal to h cap 0 plus lambda h cap dash, where lambda is some constant. Okay, and h cap dash, this is very important. The h cap dash is the perturbation term, okay, in the Hamiltonian. So this h cap dash is the part which is describing the perturbation of the system. So this is called the perturbation term in the Hamiltonian. Okay, and this lambda denotes the weight of perturbation. Okay, weight of perturbation means if lambda is very large, it means that there is a high degree of perturbation. Okay, there is a large degree of perturbation, and if lambda is small, it means that the perturbation is very small. There is only little deviation from the normal state. That is what it is actually indicating. Okay. And now we know how to express the Hamiltonian of a perturbed system. So Hamiltonian of a perturbed system is the Hamiltonian of the unperturbed system plus a perturbation term. So we can take some example of this one. Okay, we can take our previous example that we already discussed now. That is the example of the harmonic oscillator and enharmonic oscillator. So what is the Hamiltonian for the harmonic oscillator? Hamiltonian for the harmonic oscillator. Okay, harmonic oscillator. What is Hamiltonian for the harmonic oscillator? We already know that the Hamiltonian is h cap 0. Okay, h cap 0 is equal to minus h square divided by 8 pi square m d square by dx square plus potential energy, that is half kx square, right? That is a Hamiltonian for the harmonic oscillator. And for an enharmonic oscillator, the enharmonic oscillator, this Hamiltonian becomes h cap is equal to minus h square divided by 8 pi square m d square by dx square plus half kx square plus some other terms also we are going to add. That is, for example, I can add a x cube plus b x raised to 4 plus etc. Okay, so I can express the Hamiltonian like this. Okay, and here you can see that from here to here, or this part of that Hamiltonian, that is nothing but h cap 0. That is the Hamiltonian of the unperturbed system or the harmonic oscillator. And here is the additional part, and this additional part is the perturbation term. So this corresponds to lambda h cap dash. Okay, so we can represent this h cap as h cap 0 plus lambda h cap dash. Okay, so now we have an example. We have shown that the Hamiltonian of a perturbed system can be expressed in terms of the Hamiltonian of the unperturbed system. Okay, and similarly you can consider another system. For example, let us take the helium atom. Okay, helium atom. We already know that hydrogen atom is an unperturbed system. So you already know hydrogen atom. What is how you can see hydrogen atom? This is a nucleus and there is an electron, and therefore there is a nucleus electron attraction. Therefore the Hamiltonian in this case h cap 0. Okay, h cap 0 for the hydrogen atom is minus h square divided by 8 pi square m del square. Okay, plus then potential energy. What is the potential energy? That is minus z square by r, minus z square divided by r, where zd is the charge of the nucleus and minus e is the charge of the electron, and r is the distance between the nucleus and the electron. Then the potential energy is minus zd square divided by r. So this is the Hamiltonian for the hydrogen atom, and this is exactly solvable. So we can say that this is h cap 0. Okay, so h cap 0 or Hamiltonian of the unperturbed system. So this is for the hydrogen atom. And now we can consider the helium atom. Helium atom. And what is the fate of the helium atom? There is one nucleus. Okay, there is one nucleus, and let us say that this is plus Zd, where Z is equal to 2 in the case of helium. Okay, atomic number is 2, and there is one electron, that is electron 1, at a distance of r1, and there is another electron, that is electron 2, at a distance of r2, and the distance between electron 1 and electron 2 is r12. Okay, so this is the helium atom. And how can we construct the Hamiltonian for this helium atom? So let us construct the Hamiltonian for the helium atom, that is H cap is equal to minus h square divided by 8 pi square m del 1 square plus del 2 square, del 1 square plus del 2 square. Why del 1 square plus del 2 square? So this is the Laplacian operator for the electron 1, and this is the Laplacian operator corresponding to electron 2. രണ്ട് ഇലക്ട്രോണുകളുണ്ട് ഈ കേസിൽ. Therefore we have to take del 1 square plus del 2 square minus then now the potential energy term. The attractive potential energy terms are electron 1 between electron 1 and nucleus. So that is equal to minus Ze square divided by R1 minus Ze square divided by R1, where R1 is the distance between electron 1 and electron 2. The next attractive potential energy term is between electron 2 and the nucleus, and that is also minus Ze square divided by R2. Okay, and there is an electron repulsion, and that is E square plus E square divided by R12. Okay, so this is the Hamiltonian for the helium atom. And this Hamiltonian can be expressed like minus h square divided by 8 pi square m del 1 square minus Ze square divided by R1. Okay, let me put this together. Then plus minus h square divided by 8 pi square m del 2 square minus Ze square divided by R2, Ze square divided by R2, okay, R2, plus the last term is E square divided by R12. Okay, so this is the Hamiltonian. And now you look at this part of the Hamiltonian, which is inside the bracket, inside the first bracket. So this is minus h square divided by 8 pi square m del 1 square minus Ze square divided by R. What is that? We are considering the nucleus, the same nucleus with the plus Ze charge. Okay, same nucleus with the plus Ze charge, but there is only electron 1, E1 only is there. Okay, and electron 2 is kicked out from the system. So now this is a two particle system with electron nucleus and the electron 1. And if this is the system, the Hamiltonian corresponding to that will be minus h square divided by del 1 square minus Ze square divided by R1, because R1 is the distance between nucleus and electron 1, and minus h square divided by del 1 square is the Hamiltonian, the kinetic energy part of the electron 1, and therefore this one corresponds to the Hamiltonian of this particular system. Okay, this particular system. And in this particular system there is no electron 2. And therefore, actually what is this? There is one nucleus with a charge plus Ze, and then there is one electron. This is like a hydrogen-like atom, right? This is like a hydrogen-like atom that we already considered. In hydrogen-like atoms also, the nucleus has the charge plus Ze, and there is only one electron with a charge minus E, and the distance between that is R. And if that is the case, we have the Hamiltonian here, and we have a very similar system here, and therefore this is a Hamiltonian for that system. So what is it actually? If you are considering only this much, then that is the hydrogen-like system. Therefore this part of the Hamiltonian is nothing but the Hamiltonian for a hydrogen-like atom with only electron 1. Okay, so we can write this one like that is equal to h cap 0 1. Okay, h cap 0 1. Why it is 1? Because it is containing electron 1. Okay, so if there is only nucleus and electron 1, then the Hamiltonian corresponding to that system is h cap 0 1, and that system will be an unperturbed system, and that is why we have given a superscript 0 here. Okay, and now let us move on to the next one in the next square bracket. Okay, that is minus h square divided by 8 pi square m del 2 square minus zd square by r2. What is that? Now you consider there is only this nucleus and there is this electron. Okay, that is electron 2. Okay, so we are considering only this, the nucleus and the electron 2, and the distance between the nucleus and the electron 2 is r2. Okay, if that is the case, if this is the system where electron 1 is out, electron 1 അവിടെ ഇല്ല, ഇപ്പോൾ nucleus electron 2 മാത്രമേ ഉള്ളൂ, അങ്ങനെയാണെന്ന് അതിനെ ഒരു സെപ്പറേറ്റ് സിസ്റ്റം ആയിട്ട് കൺസിഡർ ചെയ്യുകയാണെന്നുണ്ടെങ്കിൽ that is also equivalent to a hydrogen like system, and its Hamiltonian will be minus h square divided by 8 pi square m del 2 square minus zd square divided by r2. Therefore, we can consider this as h cap 0 2, that is the hydrogen like system with electron 2 only. Okay, plus the last term is e square divided by r12. Okay, see now our Hamiltonian h cap is equal to h cap 0 1 plus h cap 0 2 plus e square by r12. Here these two terms are the Hamiltonian for the unperturbed system. Okay, this is for unperturbed system, and what is additional is e square by r12. So the Hamiltonian for helium atom can be constructed like the Hamiltonian for the unperturbed system plus some additional term. So this is like h cap is equal to h cap 0 plus lambda h cap dash, and here in this case the lambda h cap dash is this one. This is lambda h cap dash. Okay, that is e square divided by r12. That is a perturbation term. So now we know what is meant by perturbed systems and what is meant by unperturbed system. So there is some perturbed system, corresponding to that there is some unperturbed system also. Okay, and this perturbed system is a deviation from the unperturbed system, and this deviation can be expressed by some additional terms in the Hamiltonian of the perturbed system, and this additional term is called the perturbation term of the Hamiltonian. Okay, now you know about the perturbed systems and unperturbed systems. So now we have expressed the Hamiltonian of the perturbed systems in terms of the Hamiltonian of the unperturbed system. So in perturbation method, what we are doing in this perturbation method? In perturbation method, what we are doing is we determine the psi n and En. Okay, psi n and En. You know what is psi n and En? Psi n is the wave function of the perturbed system, and En is the energy of the perturbed system in the state En. Okay, and you determine the wave function and energy of the perturbed system in terms of, that is very important, in terms of psi n0 and En0. The wave function and energy of the perturbed system is determined in terms of psi n0 and En0, which are the wave function and energy of the unperturbed system. Okay, so how we are doing this? We will find out some correction terms to the psi n0 and En0. Okay, our system is perturbed. Because of the perturbation, there will be some correction terms, and that correction terms will be added to the wave function or energy of the unperturbed system. So let us assume that psi n1, then psi n2, etc. are the correction terms for the wave function. Okay, correction terms for the wave function. And then we can express psi n, that is the wave function of the perturbed system, as psi n 0, that is the wave function of the unperturbed system, plus okay, lambda psi n 1 plus lambda square psi n 2 plus etc. Okay, here we call this as the first order perturbation, first order correction. This is the first order correction, okay, correction to the wave function, and this is the second order correction to the wave function, second order correction to the wave function. And lambda, you already know lambda is appearing in the Hamiltonian also, because the Hamiltonian of the perturbed system h cap is equal to h cap 0 plus lambda h cap dash. Okay, so in perturbation method, what we will do is we will determine the correction terms. I will explain how we will determine the correction term later, but for the time being you understand that in perturbation method what we are doing essentially is that we are going to determine the correction terms for the wave function. Psi n1, psi n2, etc. are the correction terms, and these correction terms will be added to the wave function of the unperturbed system. The same we will do to the energy also. Okay, so if we are determining the correction terms for energy like En1, then En2, okay, En1, En2, these are the correction terms for energy, correction terms for energy. Why it is told correction term? Because for the unperturbed system there is some energy, and the energy of the perturbed system is different from that, and this correction term is added to the energy of the unperturbed system. Okay, so the energy of the perturbed system En can be expressed as energy of the unperturbed system En0 plus the correction terms, that is lambda En1 plus lambda square En2 plus etc. And this is the first order correction to the energy, and this is the second order correction to the energy. Okay, so this is what we are essentially doing in perturbation method. So in perturbation method we will find out the correction terms for wave function and energy, and these correction terms will be added to the corresponding wave function and energy of the unperturbed system, so that we will get the energy or wave function of the perturbed system. Okay, and I will explain how we will calculate these correction terms. That is what we are going to look in detail now, how to calculate the correction terms. So let us go for the calculation of the correction terms. Calculation of correction terms. How we can calculate the correction terms? So we already know that the Schrodinger wave equation for the unperturbed system. Schrodinger wave equation for the unperturbed system is h cap 0 psi n 0 is equal to En0 psi n0. That is the Schrodinger wave equation for the unperturbed system. For the perturbed system, for the perturbed system, the Schrodinger wave equation is h cap psi n is equal to En psi n. Okay, so this is a Schrodinger wave equation. Let me call this as equation number 1, and let me call this as equation number 2. Okay, and we can again expand this h cap like h cap 0 plus lambda h cap dash. Okay, where h cap 0 is the Hamiltonian of the unperturbed system, and the lambda h cap dash represents the the perturbation term in the Hamiltonian. So h cap 0 plus lambda h cap dash psi n is equal to En psi n. That is equation number 3. And I could say that H cap in on the expanded on the mathematical. Okay. And from this one, we know that if we are solving this system, and what will be the nature of the psi n and En? We already know that H cap or Hamiltonian of the perturbed system depends upon lambda, right? Lambda is here. That depends upon lambda. Therefore, the solutions psi n and En will also depend upon lambda, right? The Hamiltonian depends upon lambda. Therefore, obviously, when we are solving this system, the solution will also contain this lambda term. Or solution means wave function and energy what we are solving from this one, that is psi n and En. That will also depend upon lambda. So what we are going to do is we are going to expand the wave function and the energy as a Taylor series. Okay, so we are going to expand the wave function and energy as a Taylor series as psi n, that is the wave function of the perturbed system, is equal to psi n0, that is the wave function of the unperturbed system, plus lambda psi n1 plus lambda square psi n2 plus etc. നമ്മൾ ഇത് already ഒന്ന് mention ചെയ്തതാണ് നേരത്തെ. Okay, so this is a Taylor series, and we can express the wave function as wave function of the perturbed system as wave function of the unperturbed system plus lambda psi n1 plus lambda square psi n2 plus lambda cube psi n3, etc. Okay, you already know what are psi n1 and psi n2. This is a first order correction term, and this is a second order correction term. And the same way we can express energy En also, that is En0 plus lambda En1, let me write it better, lambda En1 plus lambda square En2 plus etc. Okay, so we can express the wave function and energy as the Taylor series like this. We are actually performing some mathematical exercise in order to solve the Schrodinger wave equation for the perturbed system. Okay, so we first express this as a Taylor series, and here you can see that there are some terms like psi nk or enk, right? Psi nk or enk, right? These terms are the kth order correction terms. Kth order correction terms. Okay, and now what we are going to do is, let me call this as equation number 4, right? This is equation number 4 and this is equation number 5. So let me substitute this equation number 4 and equation number 5 in equation number 3. Okay, you remember what was equation number 3? So this was the equation number 3, that is the Schrodinger wave equation for the perturbed system. Okay, so I am going to substitute this in equation number 3. We will substitute for psi n and En here. So what we will get after substitution, we will get H cap 0. Okay, I will do it in the next page. That is H cap 0 plus lambda H cap dash psi n, right? Now we will give the expression for psi n, that is psi n0 plus lambda psi n1 plus lambda square psi n2 plus etc. is equal to En psi n, that is En, the expression for En is En0 plus lambda En1 plus lambda square En2 plus etc. into psi n. Expression for psi n again is psi n0 plus lambda psi n1 plus lambda square psi n 2 plus etc. Okay, so we have substituted that in equation number 3. Now I am going to rearrange this equation in according to the powers of lambda. Okay, according to the powers of lambda means I am going to pick all the terms with the same power of lambda and put together. Okay, so let me take all the powers of all the terms with the lambda raised to 0. Okay, lambda raised to 0. Lambda raised to 0 means 1, or you can pick any term where lambda is not appearing. Okay, so that is lambda raised to 0, lambda raised to 0. എവിടെയൊക്കെ lambda raised to 0 appear ചെയ്യുന്നത് അല്ലെങ്കിൽ lambda ഇല്ലാത്ത terms ഏതൊക്കെയാണ്? That is h cap 0 psi n 0, this one, h cap 0 psi n 0, psi n 0. Then there is no other term here, and the other term appearing is here only, en 0 psi n 0. Okay, so that is in the right hand side, and when I am bringing that to the left hand side, I can put minus en 0 psi n 0, en 0 psi n 0. Okay, so these are the only terms without lambda. So we say that these are the terms with lambda raised to 0. Okay, plus now lambda raised to 1, lambda raised to 1 or lambda. Okay, so which are the terms with lambda raised to 1? So here is one term, that is lambda h cap dash psi n 0. Okay, so we can write lambda here also 1, h cap 0 lambda psi n 1. So let me write it first, h cap 0 lambda psi n 1. Lambda raised to 1 is already taken outside, so I can write it like h cap 0 psi n 1, h cap 0 psi n 1, and the next term will come from here, lambda h cap dash psi n 0. So that is plus h cap dash, okay, dash psi n 0, psi n 0, h cap dash psi n 0, and there is no other terms in the right hand side, left hand side, and other terms are coming from the right hand side. Okay, so here is one, en 0 lambda psi n 1. So it is minus en 0 lambda psi n 1, psi n 1. Then the next one is lambda en 1 psi n 0. So we can write minus en 1 psi n 0, psi n 0. Okay, en 1 psi n 0. And is there any other term? Okay, let me check. en 1 psi n 0, and yeah, that's all. No other term with the lambda raised to 1. Okay, now let us go for the other one, that is with the lambda square, that is lambda square into, which are the terms with the lambda square? h cap 0 psi n 2, h cap 0 psi n 2 plus lambda h cap dash into lambda lambda psi n 1. So this will also give plus h cap dash psi n 1, psi n 1. Okay, no other terms in the left hand side again, so we will pick the terms from the right hand side. Then it is minus en 0 psi n 2, en 0 psi n 2, right, en 0 psi n 2, minus then lambda en 1 lambda psi n 1. So we can pick en 1 psi n 1 minus en 1 psi n 1, then lambda square en 2 psi n 0. So we can write en 2 psi n 0 minus en 2 psi n 0. Okay, and I think it's that's all. Yeah, so we can close the bracket, plus etc., that is equal to 0. Because why it is 0? Because we have taken all the terms all the terms in the right hand side are taken to the left hand side, right? So this is equal to 0. We no need to give equal sign here. Okay. Yeah. Is equal to this. Yeah. This is equal to 0. Okay. Sorry. I was thinking that this is also part of the last equation. Okay, so equals here. So this one, our equation begins from here. Okay, our new equation begins from here. See, lambda 0 into this one, then lambda 1 into this one, and lambda square into this one, that is equal to 0. Okay, so this is our equation. And now we have an equation with the different powers of lambda, and the right hand side of this equation is equal to 0. So how this equation can be true? This equation can be true if the coefficients of each powers of lambda is 0 individually, right? The lambdas cannot be 0. Lambda cannot be 0 because if lambda is 0, it means that there is no correction term. Lambda 0 ആണെന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ എൻ്റെ അർത്ഥം എന്താണ്? കറക്ഷൻ ടേംസ് എല്ലാം വാനിഷ് ആയി പോകും. കറക്ഷൻ ടേംസ് എല്ലാം വാനിഷ് ആയി പോകുന്നത് പറഞ്ഞു കഴിഞ്ഞാൽ നമ്മളുടെ പെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ വേവ് ഫംഗ്ഷൻ എന്ന് പറയുന്നത് അൺപെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ വേവ് ഫംഗ്ഷൻ തന്നെയാകും. അല്ലെങ്കിൽ പെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ എനർജി എന്ന് പറയുന്നത് അൺപെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ എനർജി ആകും. പെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ ഹാമിൽട്ടോണിയൻ അൺപെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ ഹാമിൽട്ടോണിയൻ ആകും. എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ സിസ്റ്റം പെർട്ടർബ്ഡ് അല്ല എന്നർത്ഥം, അല്ലേ? സോ ലാംഡ വിൽ ബി 0 only in the case when the system is not perturbed. പക്ഷെ നമ്മൾ പെർട്ടർബ്ഡ് സിസ്റ്റം ആണ് പരിഗണിക്കുന്നുണ്ടെങ്കിൽ ലാംഡ ക്യാൻ നെവർ ബി ഈക്വൽ ടു 0. ഓക്കെ, സോ ലാംഡ ഈസ് നോട്ട് 0. ലാംഡ 0 അല്ലാത്തത് കൊണ്ട് ഇവിടുത്തെ ലാംഡ ടേംസ് ഒന്നും 0 അല്ല. ഈ ഇക്വേഷനിലെ ലാംഡ ടേംസ് ഒന്നും 0 അല്ല. നൺ ഓഫ് ദ ലാംഡ ടേംസ് ആർ ഈക്വൽ ടു 0. ദിസ് ഈസ് ഓൾറെഡി 1. ലാംഡ റൈസ് ടു 1 cannot be 0 and ലാംഡ റൈസ് ടു 2 cannot be 0. Then what is the next possibility? The possibility is that the terms inside these square brackets, those terms should be equal to 0. That is only one possibility. അങ്ങനെയാണെന്നുണ്ടെങ്കിൽ മാത്രമേ റൈറ്റ് ഹാൻഡ് സൈഡ് 0 ആയിട്ട് വരത്തുള്ളൂ, അല്ലേ? So this equation is true only if the coefficients of each power of lambda is 0 individually. Okay, so that we have to consider next. So for lambda raised to 0, we can understand that from this equation, h cap 0 psi n 0 minus en 0 psi n 0 is equal to 0. Okay, let me write it there. H cap 0 psi n 0 minus en 0 psi n 0 is equal to 0. This equation is nothing but h cap 0 psi n 0 is equal to en 0 psi n 0. You remember this equation. This was the Schrodinger wave equation for the unperturbed system, right? And for lambda raised to 1, so what will be the case for lambda raised to 1? Let us pick the coefficient for lambda raised to 1. This is the coefficient for lambda raised to 1. That is h cap 0 psi n 1 plus h cap dash psi n 0 minus en 0 psi n 1 minus en 1 psi n 0. That is equal to 0. So let me write it there. That is h cap 0 psi n 1, isn't it? H cap 0 psi n 1. So you can remember this just like this, right? 0 and 1. Okay, in this case also 0 and 1 and 1 and 0. Okay, so like that. And h cap 0 psi n 1 plus h cap dash psi n 0 plus minus en 1 psi n 0 minus en 1 psi n 0 minus en 0 psi n 1. Okay, psi n 1, and that is equal to 0. Okay, that is equal to 0. And for lambda square, or we can rearrange this once again like h cap 0 h cap 0 psi n1 plus h cap dash. We can put this psi n1 together. Okay, h cap 0 psi n0 minus en0 h cap 0 psi n1 minus en0 psi n1. Psi n1 terms together. So we can write it like h cap 0 minus en0 minus en0, okay, psi n1 is equal to, okay, this one will go to the other side, those minus h cap dash psi n0, then plus en1 psi n0. Okay, so this is a new equation. And now let us go for lambda square. For lambda square, the coefficient of the lambda square in the previous equation, okay, this one, this is equal to 0. Okay, so that is, for lambda square we can write like h cap 0 psi n2 plus h cap dash psi n1, right? H cap 0 psi n2, h cap dash psi n1. All other terms are minus signs. That is en0 psi n2, en1 psi n1, en2 psi n0. Okay, it's very easy to remember. 0, 2. So 0 plus 2, 2. 1 plus 1, 2. 2 plus 0, 2. Okay, you can remember like that. Okay, so we can write like minus en0 psi n2, en0 psi n2 minus en1 psi n1 minus en2 psi n0, that is equal to 0. That is equal to 0. Okay, and from this one we can write again another equation, that is, let me pick another color, that is h cap 0 then I am going to pick psi n2 terms, psi n2. Okay, here h cap 0 minus en0 psi n2 minus en0 psi n2 is equal to minus h cap dash psi n1 minus h cap dash psi n1, sorry, psi n1, then plus en1 psi n1 plus en1 psi n1, right? en1 psi n1 plus en0 psi n2, okay, plus en0, okay, this step I forgot to put this one, no, sorry, en1 psi n1 plus en2 psi n0, okay, sorry, en2 psi n0, en2 psi n0. Okay, so we have another equation here. So now we have three equations. Which was the equation that we used? What was the number we used last? This was equation number 5. Okay, and this is equation number. We can equation number 7, and this is equation number 8. This is equation number 9, and this is equation number 10. Okay, we put like that. So you can see that the equation number 8 is the Schrodinger wave equation for the unperturbed system. Okay, and from this one, by solving this one, you get the wave function and the energy for the unperturbed system. Just by solving this equation, you will get the wave function and energy for the unperturbed system. So now you have psi n0 and en0. Okay, by solving the Schrodinger wave equation for the unperturbed system, you have psi n0 and en0. So let me write it there. You have psi n0 and en0. Okay, this you can get by solving the Schrodinger equation for the unperturbed system, and you have the Hamiltonian for the unperturbed system. You have every knowledge of the unperturbed system. Okay, so this is already known. Because you already have the knowledge of that. And if we are checking the other equations, see, this is an equation for psi n1, psi n1. That is the first order correction to the wave function. Okay. And here you can see another term en1 also. Okay. So by solving this equation, you will get psi n1 and en1, but that will be in terms of psi n0 and en0. Okay. So you will get psi n1 and en1 in terms of psi n0 and en0. So by solving the equation number 9, solving equation number 9, you get psi n1 and en1 in terms of this, that is psi n0 and en0. Okay, in terms of psi n0 and en0, and psi n0 and en0 are already known. So you get the first order correction to the energy, first order correction to the wave function, and first order correction to the energy. Now if you are going for the next one, okay, the next equation, that is equation number 10, then you can get the expression for psi n2 and en2, and this will be in terms of psi n1. Okay, this will be in terms of psi n1 and en1, or psi n0 and en0. Okay, so you get the expression for psi n2 and en2 in terms of psi n1, en1, psi n0 and en0. Okay, so let me write that there. By solving equation number 10, you get the expression for psi n2 and en2, but in terms of what? In terms of psi n1 and en1 and psi n0 and en0. Okay, when you are in this step, you already know psi n0, en0, and already you know psi n1 and en1. Like equation number 10, we solve already psi n1 and en1 expression. Therefore, when you are solving equation number 10, you will get a new expression for wave function and energy that will be in terms of already known expressions for the wave function and energy. Okay, so like that you find out the second order correction to the wave function and energy. So you find out the first order correction, second order correction, you can go on and find out the third order correction, fourth order correction, etc. But it is actually not needed in most of the case. In most of the chemical problems, we deal in the problems, or second order correction vare namakku avashyullu. Okay, we don't need to go for the third order correction or fourth order correction in the chemical problem that we are usually dealing with. Now, we can en2, en2 vare kandupidicha madi sadharanagari. Now, iduvare aayi kazhinjal, now we can get the expression for psi n and en. Now we go for the expression for psi n and en. What is the expression for psi n? Psi n is the wave function for the perturbed system, and that psi n is equal to psi n0 plus lambda psi n1 plus lambda square psi n2, right? And en is equal to en0 plus lambda en1 plus lambda square en2, right? We can write like this. So now by finding out the wave function, the first order correction and second order correction to the wave function and energy, you can get the expression or the expression for the wave function and energy of the perturbed system, that is in terms of the corresponding wave function and energy for the unperturbed system. And this is essentially the perturbation method. This is perturbation method. Okay. But perturbation method is perturbation method we must have the knowledge of the unperturbed system. Unperturbed system prior knowledge. Prior knowledge നമുക്ക് പെർട്ടർബേഷൻ ട്രീറ്റ്മെൻറ്റ് നടത്താം. അപ്പോൾ നമ്മളുടെ സിസ്റ്റത്തിൻ്റെ പെർട്ടർബേഷൻ ഹാമിൽട്ടോണിയൻ നമ്മൾ കൺസ്ട്രക്ട് ചെയ്യുന്നു. അങ്ങനെ ഹാമിൽട്ടോണിയൻ കൺസ്ട്രക്ട് ചെയ്തതിനു ശേഷം നമ്മൾ ഇപ്പം ചെയ്ത രീതിയിൽ നമ്മൾ ഫസ്റ്റ് ഓർഡർ കറക്ഷനും സെക്കൻഡ് ഓർഡർ കറക്ഷനും നമ്മൾ കണ്ടുപിടിക്കുന്നു. അതിനുശേഷം ഈ ഫസ്റ്റ് ഓർഡർ കറക്ഷനും സെക്കൻഡ് ഓർഡർ കറക്ഷനും നമ്മുടെ അൺപെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ കറസ്പോണ്ടിങ് ഫംഗ്ഷൻസുമായിട്ട് നമ്മൾ ആഡ് ചെയ്യുന്നു. അപ്പോൾ നമുക്ക് പെർട്ടർബ്ഡ് സിസ്റ്റത്തിന്റെ വേവ് ഫംഗ്ഷനോ അല്ലെങ്കിൽ എനർജിയോ കിട്ടുന്നു. ദിസ് ഈസ് ദ പെർട്ടർബേഷൻ മെത്തേഡ്. Okay, I hope you understood the essential idea of the perturbation method, and in the next class we will continue with the first order correction. We will go in detail of the first order correction for the wave function and energy. And ഇതിൻ്റെ എസെൻഷ്യൽ ആയിട്ടുള്ള കാര്യങ്ങൾ നിങ്ങൾക്ക് മനസ്സിലായി എന്ന് വിചാരിക്കുന്നു. എന്തെങ്കിലും സംശയമുണ്ടെങ്കിൽ, if you have any doubt, please don't hesitate to ask me. Thank you for watching and stay tuned.